Okay, today's topic we will continue in the latch. Then we will discuss also the flip-flops. So the overall, we discussed so far three types of latch. There is SR latch, SR with enable or with gates, and there is D flip-flop with gates or enable. I'm sorry, D latch. All of them are latches. In SR latch, when S equals 0, R equal 1, we are in resets. When S equal 1, R equals 0, we are in sets. Means Q equals 0, here set Q equal 1, S equals 0, R equals 0, we are in hold, so Q will equal to Q, which is the old status. S equal 1, R equal 1, it's forbidden states. That's for the first one. For the second one, SR latch with gates, when G equals 0, we are on hold. No matter what's R, no matter what's S. Don't care. If G equal 1 or enable equal 1, then normal SR latch. Okay? We already discussed this last lecture. In D latch, depending on the gates, when G equals 0, we are on hold. When G equal 1, then Q will be D. So I can say on hold, Q will be Q, and Q will be D. So in order to distinguish between Q old and Q new, I can write it as Q star equal to Q, such that Q star is the new one. Or I can write it in other format like Q of T plus 1, which is the future Q, will equal to Q of T. And here the other one, Q of T plus 1 equals to D. So no matter if I write it as in star forms or in a Q of T plus 1 and the Q of T, this should be the same. So as a shortcut, instead of drawing SL latch like this or D latch like this, multiple of AND gates or NOR gates, etc., then we write it in this graph, like this block. So here's block, this is the input of S, this is the input R, here's Q, here's Q, but there's a bubble, this means Q bar. Sometimes as a shortcut, some textbook you will see, we write Q and the Q here, or some of them we eliminate them. So we just understand them, we can understand it like this way. Then, by looking at this Q here, we will realize that there is sometimes based on AND gates or based on NAND gates or NOR gates or based on NAND gates. So whenever we see the first symbol this way, this based on NOR gates. In other words, this is active high. However, this part, how did I know there is S bar or R bar? There is a bubble at the inputs. This means this is based on NAND gates. Then this is active low. So by looking at the symbol, you need to realize, is this one active high or active low? If there is any bubbles at the inputs, this means this is active low. Otherwise, the default is active high, which is based on NOR gates. Then for the D latch, like this way, there is enable and there is D. Then we can realize this symbol is based on active high. Why? Because there is no bubbles at the inputs. In case if there is bubbles, again, it will be active low. Okay? Any question? And we already discussed several timing diagrams, how to solve the timing diagram for each type, SR latch or D latch or SR with gate latch. Then we already are aware how to deal with latch, which is how to store the data. So we can store the data into different sets of latch. So we can, for example, convert this information into digital logic, into all like make it as zeros or ones, or store it in bytes. Then each byte has 8 bits. Each bit will be stored in one latch. It can be D latch or it can be SR latch. But we will realize there's a problems actually associated with latches. So even though the latches are okay, can work fine, but there are some problems depending on the gates or into the enable gates. So these enable gates, sometimes we can connect them into a clock pulse. So that clock pulse will tell you when to update the next data. As I mentioned, like tick, tock, tick, tock. At each tick, I want to make an update. So sometimes in the latch, it will not be updated. It will be updated based on the level. What do I mean by level? Like, let's assume this is a pulse. This is the clock pulses. For the latch, it will be active during this period. So let's assume that I want to store a certain data. So that data stored, it will be taken into consideration during the on time. Then if there is any changing happening here, it will detect this. And it will take this change. But if I need to store this data and make it on hold, then any change happening here inside the on time or during the on time, this will be with latches. Therefore, if we are working with asynchronous, something not related to the clock, then the latch can be fine. But if we are working with synchronous, which means the clock makes sense with us, then any change happening here might be detected, and sometimes it can be something undesired. So here in sequential or in this kind of circuits, sequentials, and there is, as I said, like synchronous, we have a clock pulses, and in the latch, it will respond, as mentioned here, to change in the level of the clock pulses. So it will change, as I mentioned here, this is the clock pulses, so it will work during the on time. However, the clock pulses has two transitions. Because again, the pulses, it can be on, off, on, off, on, off. So in real life, there are two transitions. There is transition from high to low, then from low to high. And there is a level in the middle. So the latches will be associated with the level. If it is at on, then if we are at on time, it will detect everything, keep detecting, keep monitoring. But we create something is called flip-flop that will work either on transition high to low or transition low to high. And this region will be flip-flop. So we created the flip-flop such that it will be updated once, not updated during a period of time. So whenever the clock, for example, go from high to low, update the system. Don't keep detecting. Updating only once. It's not like, again, the latch will detect during the whole on time. Like I'm gonna write like something here. Here is the clock cycle. Then let's assume here's the clock. This is D, for example. In D, some changes can happen. So the latch, Q with latch, what will be? In latch, it will detect during the whole on time. So during the on time, it will detect everything. Then during the off time, it will hold. Then here on time, will detect everything. So the latch, again, it detects this, then hold. Here, Q equal D, then here is hold. That was in the latch. However, in the flip-flop, our target is to look at, let me assume, like rising edge. Flip-flop, we need to detect only during the positive cycle. During the, we call it, the transition from low to high. This is called rising edge, or here, transition from low to high. So at the transition from low to high, you will realize D was on. So here, for example, it will be 0, then it will be on. Then it will keep on, hold, until the next status. This will be off, 0, then it will be 0, and so on. So we will see that the latch will be updated only, or the flip-flop will be updated only once. While the latch, it will be updated, you will keep monitoring what's happening inside here. That was the latch. But the flip-flop will only detect if it is either rising edge or falling edge. Okay? So here, in this scenario, I assume it's rising edge. It can be falling edge as well. So, again, the clock pulse, there are two transitions. We can detect either this one, but the latch, it will respond to any change during the on time. So sometimes that can create a problem for us, especially if we need to detect some data, and this information will not be guaranteed to be continuous. So let's assume that we are receiving some wireless data, and that wireless data that we detect, we need just to detect this signal and keep it hold. How about if during this clock cycle, if the signal will be changed, or if this wireless signal will be eliminated for some reason? So if we don't have enough time, this data will not be stored correctly. So in order to store the data correctly, we realize that we need to use only single transaction or single trigger. Only one single transaction that can detect this, or updated it only once each clock cycle. That's our target, is to update look at the memory once each clock cycle. So we can update it either using positive edge or negative edge, but we don't want to keep updating this during the on time. Therefore, we generated the flip-flop, or we created something called flip-flop. Again, in latch, that's what's happening. In flip-flops, there are two types. There is rising edge or positive edge, or there is negative edge. So sometimes we call it rising, this falling edge. This will be associated with flip-flops. Sometimes flip-flops shortcut FF for flip-flops. Therefore, since the latches are updated during the on time, this makes something less likely or undesired or less likely to be used. Therefore, why in real life we have flip-flops more than latches. Latches can be used again if we have if the enable, or if the gates, or if the clock is not the clock that we see, clock tick-tock. If it's a clock like as a counter, I can control it. Then this will be something different. But here, if we are dealing with synchronous, then most likely what's preferred to use is to use flip-flops. That's what's used in real life. Used in real life. So again, our target is to update it once, not to keep updating this. So it can make the problem easier. How to create the flip-flop? Actually, we can create the flip-flop, for example, D flip-flop. It's actually based on D latch, and it's a combination of two D latches in parallel. In series. Then we can create the flip-flop. Then we are trying to make the problem as getting more complicated, or step by step. So first, I start discussing about how to create the memory, or how to store the data by having two inverters. Then we replaced one of these by NOR gates. Then the other one by NOR gates to create SR latches. Then we added enable. Then we said S and R, something undesired because we have a forbidden state. Then we can create D latches with enable. Then after that, we said the latch is not preferred, then we need to create flip-flops, which is a combination of two latches. Then we are making the problem or trying to make like climbing the hill, going more complicated step by step. If you're not understanding the latch very well, then maybe you'll struggle with the flip-flops and so on. So please make sure to be up to date. Here, like flip-flops, as a shortcuts, you are not required to memorize what's inside, like draw the equivalent circuits of flip-flops in latch, or draw what's inside the latch, convert the latch to NAND gates or NOR gates, because I don't believe memorizing this will benefit you. Maybe when you will be like later a programmer, you will go to the data sheets, then you will see everything in the data sheet. So if you memorize something, you will forget it maybe after 1 week. So I don't think there is a point of memorizing these equations or these circuits, equivalent circuits. Therefore, we can replace the D flip-flop this by a box or an equivalent box. This equivalent box can be drawn like this. So here is D latch, here is the clock cycle, here is Q, here is Q bar. You can add either Q bar here or make a bubble. It's up to you, but don't make both. So it's actually the same as D latch, right? The same one. But there should be a difference that make it distinguish this. So is this one flip-flop or all latch? By looking, there's more triangular shape here. Then right clock. Rectangular, rectangular or triangular, I'm sorry. Why am I saying? Apologize. There should be a small triangular shape here. Then definitely you will say this is flip-flop. That's how I distinguish. While the latch, you will not see triangular. So I mentioned about the flip-flop here, it can be either rising edge or falling edge. The default is rising edge. While if it is falling edge, should be a bubble. So let me write these two representations. Here is D, here is clock, here is Q, here is Q bar, here is D, here is bubble, here is clock, here is Q, here is Q bar, here is D, here is gates, this Q bar. Okay, so the first one is D flip-flop and rising edge, or positive edge sometimes we call it. Either way, it should be the same. The other one, I think I forget to write the triangular shape here. It's flip-flop because there's a triangular shape, and since there is a bubble, it's falling edge. D flip-flop, falling edge. Okay? The last one, it's D latch. Why? Because there is no triangular shape into the clock. Okay? The overall equation of the flip-flop, Q of T plus 1 equals to D, the status of D. This is at trigger or at falling edge or rising edge. Otherwise, halt. Okay? So whenever, like this is the clock cycle, it will update only at these points. Q equal D, Q equal D, Q equal D. And the rest, what's happening between them, will hold. The rest will be hold. Okay? Does this make sense? So you need, when we determine it's rising edge or falling edge, we will say that at this edge there will be updates. Otherwise, hold. There is no forbidden status. There is no other tricky status. So actually dealing with flip-flops will be much easier than dealing with latch, because in latch you need to detect what's happening inside the on time. But here, don't worry about it. Let's imagine we have this. This clock, and this is the inputs. We have this one based on latch, the other one based in flip-flop. And let me assume a rising edge. I'm going to assume the initial condition 0. Okay? So we can have a clue that it will start from 0, it will start from 0. So the first step, in order to determine the flip-flops or either latch, like locates where are the changes. So let me do the flip-flops first, because the flip-flops are much easier than the latch. So in flip-flops, it's rising edge. Rising edge happening here, 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 here. So only at these 5 arrows, there will be updates. The rest will be hold. So what's happening for key flip-flop, it will start with 0, then here updates, D is 1, then it will go to 1. Then hold. Updates, D is 0, it will go to 0. Updates, D is 0, it will go to 0. Updates, D is 1, it will go to 1. Updates, D is 0, it will go to 0, and that's it. So doing D flip-flop is much easier than latch. How to do the latch? For doing the latch, you need to determine the other boundaries. So, like for example, this boundary, because during the on-time boundary, and you need to detect also what's happening between the on-time. So here there is no change between the on-time. This is the on-time, there is this change. This on-time, there is this change. This on-time, there is change. And here there is another change. So look at the on-time on the clock pulses. This is the on-time, this is the on-time, this is on-time, on-time, on-time. And see if there is any change on D on it. After that, we can say we're ready to draw. So let's start drawing. I'm going to draw it. So here it will start with 0. Then here the change will happen inside the clock cycle. So inside the clock cycle it will be on. Then here it will hold until the next clock cycle. Then it will copy what's happening with D. Then it will hold. Then in this cycle it will copy what's happening with D. Then it will hold. Then it will copy what's happening with D. Then hold. Copy what's happening with D. Then hold. So you see, like the latch and the flip-flops, even though they are the same type D, but they will be different. Yes?
Can you explain why on the flip-flop, on the middle rising edge, it doesn't flip-flop?
Which one here?
So on QFF.
Yes.
So the middle red.
Do you mean this one?
Yeah, what is that not flip-flop?
Okay. Let's see. So the first one, rising edge, D is 1, therefore it is 1. Then let's go. So you agree with the first one, right? Let's go to the next one. So it will hold on until go to the next one. Next one, this goes, D is 0, then it will move to 0. Right? Then we'll keep going to 0. Then in third one, the next updates, D is 0, therefore it will keep 0. So let's go to the fourth one. Fourth one, D is 1, therefore it will go to 1. So the update's happening only at the flip-flops. Then the last one, D is 0, therefore it will be 0. Okay? Any other question? Okay. So again, rising edge or falling edge, if there is any bubble, this means falling edge. If there is no bubble, this is rising edge. And this is how the circuit looks like of the rising edge in terms of, not the flip, in terms of NAND gates or NOR gates, NAND gates or NOR gates. So you can, basically that's how we implement this. So we will assume, again, we will not keep using NAND gates or NOR gates. We can build our modules, it's called flip-flops, and build an IC, it's called flip-flops. So we will use this IC instead of every time drawing NANDs and NOR gates. So we will just use the simple, this one, and that's it. So this will make it much easier for us other than dealing with this. So we can simplify all of these by using a ready module. Okay, so here's explaining the situation. Okay, we already discussed this. So the function Q of t equal to 0. Basically, this thing called like truth table, or sometimes we call it excitation table. There's another way, like in the textbook, it's written excitation table. It can be written as here is D, here is all the Q, here is a Q star, or sometimes we call it QT plus 1. So we have, it can be 0, 0, 0, 1, 1, 0, 1, 1. Then, if we have D is 0, this will make it hold. Therefore, it will be 0. If D is 0 and the Q is 1, this means we are Q equal D. Then Q will be 0. If D is 1 and the Q is 0, this will hold. Will keep, means the Q star will equal to Q. Q star will equal to Q. So which is, make it as 0. I'm sorry, we'll make it, yes. If D is 1 and the Q old is 1, this will make it 1. Let me make sure if I did it correctly. If D is 1, Q is 1, this will make it 1. This will make it Q star equals to D. And D here is equal 1, then this will be 1. That's what will be 0. Okay? Then later, let me make it 0 and 1. What will happen here? I think I get confused with something, because there should be an enable as well. Q equal to Q star, because the function Q of t equal to D. Yeah, I didn't mention anything about the pulses, so let me redo it again. I'm sorry, I apologize. Okay, let's do it again. Because there is an enable, I was talking about the enable. Let me do it again without looking at the enable. Okay, again. I'm sorry about this. Q equal to D. So no matter what's Q here, it will remain as D. So it will be 0, 0, here D 1, 1. That's it. Well, I get confused in the beginning because I assumed as D or as enable and Q. This will be different. If it is enable and Q, this will be right, what I mentioned in the past. So if 0, 0, or if enable, I can write it without this part. I can write it as enable here. If enable is 0, then Q star equal to Q. If enable equal to 1, then Q of t equal to D. Okay? Any question? Okay, here I keep repeating positive edge and negative edge. Look at the bubble, locate where it is. And there's a triangle shape. This makes it flip-flops, not latches. Now, can we modify on SR latch, get SR latch to be a flip-flop, SR flip-flop? Yes, we can. So here is a modification. We can modify on SR flip-flop, SR flip latch to be SR flip-flop. So basically, it's the same as we used to know earlier, like rising edge or falling edge. Here is S, here is R, here is clock, and here is Q, here is Q bar. So this one, since there is a triangle shape, this is flip-flop, SR flip-flop. This SR flip-flop as well. But the difference between them, this is rising edge. And this is falling edge. Okay? The same as SR latch. But keep in mind the updates will happen either in falling edge or in rising edge. So if we need to draw the execution table here, if we have S and R zeros, S equals 0, R equals 0, then it will be in hold states. S equal 1, R equal 1, we will be in resets. S equal 1, R equals 0 will be in sets. Both of them ones is not allowed or forbidden states. Therefore, in this scenario, Q star here, let's assume Q sometimes 0, sometimes 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. So it will hold. This means Q star will equal to the old Q. Therefore, it will be 0, 1. Resets means Q star will be 0. So no matter what's the Q, it will be zeros. Set means Q star will be 1. This will make it 1, 1. Not allowed, forbidden states. Okay? So it will be the same way as we used to do with SL latch, but keep in mind the updates happening at either rising edge or falling edge. But we still have this thing, which is something undesired. Not allowed or forbidden states. The forbidden state is something undesired. Now, can we cancel this state or remove it? Because, again, the SR latch or SR flip-flops, there's a forbidden state that's something undesired. Maybe during my programming or during my analysis, I don't want every time to forbid or avoid this. This sometimes can confuse me or can confuse. I'm sorry. So, what shall we do? We need to remove this. How can we remove it? There is a new modification that can be done on SL latch by modifying on this state, but we will not do it as not allowed. Because in SL latch, again, there is in SR latch or SR flip-flops, there is Q equal to Q star. There is Q equal 1, there is Q equal 0. These are the cases. Now, if we need to remove it, we still need, and there's a forbidden state, of course. We still need Q equal Q star. And we still need Q equal 1. We still need Q equal 0. So what's the possible solution to remove the forbidden states? And we need to be in the same sequence. We don't want to make it 0 because 0, we already have the states of 0. We don't want to make it 1 because we already have the status of 1. So we have Q equal Q. Is there any fourth option that I can add to remove the forbidden states? What do you think this option will be? Remove an option, but I don't want to repeat the scenario. Yes?
Q bar.
Q bar, right. We can make Q bar because I want to be in the same sequence, but I don't want to repeat 0 and don't want to repeat 1. And you want to repeat Q. The other solution is Q bar because we already have Q, then the opposite of Q is Q bar. So we can say, I think I am between this here. This is star, this star, this star. So we can say, let's replace that Q by Q bar, or replace the forbidden states to be Q bar. In that scenario here, S equals 0, R equals 0. Here is S equal 1, R equals 0. Here is S equal 0, R equal 1. Here is S equal 1, R equal 1. So we can say that when both are 1s, we can create something or replace it to be, instead of forbidden state, to be Q equal to Q bar. Can we do this? Yes, we can do. How? We can modify the circuit so it can be done. The digital logic circuit to be done. Okay, so what should I call this one? Should I call it SR flip-flop modified or modified SR flip-flop? You can call it like this, but in digital logic, we don't prefer this. So we don't want to distinguish it. Therefore, we replace this from SR flip-flop to be called JK flip-flop. So JK flip-flop is the same as SR, but remove the forbidden. Then we will call it JK flip-flop. Such that here is the same as SR latch, but we will call it J instead of S. S will be replaced by J, R will be replaced by K. So J equals 0, K equals 0, the first part. The second part, J equal 1, K equals 0. Here is J equals 0, K equal 1. Then in both, when J equal 1, K equal 1, we will no longer, its forbidden state, it will be Q bar. So we can distinguish, or we don't want to get confused between this and SR. So if I said here, SR, if S equal 1, R equal 1, Q equal B, Q bar, you will get confused between this and the SR flip-flop or SR latch. Therefore, we created another version, make it another name, while it's the same function but with modified version. Then we call it JK flip-flop. So again, JK flip-flop is a modified version such that S equal 1, R equal now is allowed. But we will no longer call it S equal 1, R equal 1. We will call it J equal 1 and K equal 1. Then it will be, we call it toggle mode or complement mode or Q equal to Q bar. So we have we have 4 modes, or actually, yeah, we have some modes of operation like sets, reset, complement, or keep it like as is. So the function here, when J equals 0, K equals 0, no change. J equals 0, K equal 1, resets. J equal 1, K equals 0, sets. Both ones, this will be in complements. So this is, it looks like we replaced S to be J, we replaced R to be K. That's it. So how can we create a function? We realize that we can create a function as J Q of T plus 1 equals J Q bar plus K bar Q. That's the function of the flip-flop. Sometimes we can say Q of T plus 1, or sometimes we can say Q star. So this is the governing equation. So in case that if you missed, if 0, 0 should be Q or should be something, then you can just apply this formula. So we can apply it that if J equals 0 and K equals 0, this will make it 0 Q bar plus 0 bar Q. This will make it 0 plus 0 bar, which is 1, which will make it a Q. That's how we can derive it. So if you memorize the formula, you can find the execution table easy. Okay, that's how the flip-flops looks like inside. It's basically SR latch, but we add SR flip-flop, but we add 2 AND gates to make it to remove the forbidden states. So it's basically based on SR flip-flop. Just put some AND gates. So this JK flip-flop with rising edge. How about falling edge? You can draw it like J, K. Here is the clock, and put a bubble. Then we can realize this is falling edge. JK flip-flop, falling edge or negative edge. Or in other words, negative edge. And that one was positive edge. Okay? So you need to look at the symbol and realize, is this latch, is this flip-flop, is this JK flip-flop, SR latch? Just look at the symbol and then you should memorize, you should know how to deal with this. How to try the execution table into the other representation. Again, Q star equal JQ bar plus K bar Q. So number of 0, 1, 0, 1, 0, 1, 0, 1. So when J equals 0, K equals 0, we are in hold mode, so it will be copy was Q. When J equal 0, K equal 1, we are in reset, so will be zeros. When J equal 1, K equal zeros, we are in zeros, so there will be, we are in 1, so it will be in set, this will be 1s. Then J1 equal K1, which is in the complement mode, so it will be 1, 0. Again, here I draw it based on my understanding or how I understand the flip-flop. If you don't want to do this, or sometimes if you're afraid to get confused, use this formula, you will get the same answer. Try substitute 0, 0, 0, you will get 0. Substitute 0, 0, 1, you will get 1. Substitute them here. Substitute 0, 1, 0, substitute it in the equation, then you can get it. Or if you want to verify your answer. Let's verify, for example, the last one. If 1, 1, 1, will I get 0? Let's see. It will be 1, and the Q bar will be 1 bar plus 1 bar, 1. This will make it 1 times 0 plus 0 times 1. Then we'll make it 0 plus 0, then we'll make it 0. That's what we get, 0 here. Okay? Then you can apply the same for the rests. That's how we find the excitation table. So now, so far, we know D flip-flop, we know SR flip-flop, JK flip-flop, which is the modified version of SR flip-flop. Let's recall also the latch. The latch, we know the SR latch, gated SR latch, then D latch. When we created the D latch, we said, we don't want to have two inputs, S and R. How about if we mix them and make them one? Then we created the D latch, right? Do you remember this? Now, for the same of the flip-flops, for now the modified SR flip-flop, which is called JK flip-flop, can we make J and K the same inputs? Yes, which is I don't want to have too many inputs. If we make them with one, it will not be D flip-flop, because D flip-flop is based on D latch. So it will not be called D flip-flop. It will be another version. And this thing is called T flip-flop. So T flip-flop is a modified version of JK by making J equal K equal to T. So we will replace J and K by a symbol called T. This is another version. Therefore, the symbol, it will be T Q bar plus T bar Q, and it's the same as exclusive OR, which is T exclusive OR with Q. So you have the option to use exclusive OR, or you can say it's just T Q bar plus T bar Q. Then T flip-flop is easier than JK because we have only one inputs. Okay? So we see like we are like climbing the hill, like trying with start with the simplest, go more complicated, but if you understand the basics, it will be easier to understand next. So if you're not understanding the JK flip-flop, you will not understand the T. If you're not understanding also the latch, you will not understanding the flip-flop, and so on. So please make sure when you go back home during the weekend, review all of these analysis, like JK flip-flop, T flip-flop, and be aware of all of them. So the execution table, it's T and Q. So basically, we can say if T equals 0, we have T Q bar plus T bar Q. This is Q star. So we can say Q star, if T equals 0, this will make it Q star equal to Q, which is hold. If T equal 1, here's T equals 0. If T equal 1, then Q star will equal to Q bar, which is in complement mode. So we don't have set or reset mode. We have either hold or complement, hold, complement, hold, complements, or reverse. So we can say here is 0, 1, 0, 1. Then when T equals 0, we are in hold, which is Q equal to Q star. Then it will be 0, 1. When T equal 1, we are in complement mode. So Q star equal to Q bar. Okay? Then 0, 1 will be 1, 0. This is one way, by understanding the concept of flip-flop. Or the other way, by applying the exclusive or applying T Q bar plus Q bar T bar Q. So by applying the exclusive OR, look, if there is odd number of ones, make it 1. If there is even numbers or none, make it 0. So here there is none, then make it 0. There is odd number, make it 1. Odd number, make it 1. Even number, make it 0. This is another way. Okay, so you need to understand it in two ways. One of them in understanding the way of flip-flops, the other way in understanding of digital logic circuits. In summary, we have like 3 main flip-flops, which is JK flip-flop, D flip-flop, T flip-flop. However, the SR flip-flop are not used in real life, because the JK flip-flop can do the job of SR, right? And the forbidden state is something undesired. Therefore, SR flip-flop is not used in real life. Maybe just a concept. It's very seldom to see like SR flip-flop. Even in some textbooks, you will not see SR flip-flop at all. It's not mentioned in the concepts, because most likely it's already covered in JK flip-flop. So the characteristic of flip-flops that you need to write this in your note card for the test, which is you need to know that JK flip-flop equation, Q of T plus 1 or Q star, is actually J Q bar plus K bar Q. Then in T flip-flop, that QT plus 1 will be T Q bar plus T bar Q, or in other words, T exclusive OR with Q. Then in D flip-flop, which is the simplest, Q of T plus 1 equal to D. So these 3 equations, you need to memorize them or write them in your note card, because these are very essential for what we will see later. And they are actually written, I think, here. Yeah, they're already written here, so. While for the SR flip-flop, again, it's not common. But in case if you need it, if you need the equation, it will be the same as JK flip-flop. But keep in mind the last step, which is 1, S equal 1 and R equal 1, is forbidden, which is not allowed, and didn't do it. Then, while they are almost the same. Okay? Okay, determine Y1, Y2, Y3 for this timing diagram. Okay, before discussing this example, I encourage you to go to, there is a notes, additional notes, timing diagram, additional examples. Here, summarize everything related to the latch and related to the flip-flops. Okay, so this is SR latch with gated. Look at the clock. Let's assume the SR like this. Here. Here is S and the R. Like this. Let's assume the initial condition is 0. So since we are dealing with SR latch, gated SR latch, you need to look at the clock edge boundaries. There is no rising edge or falling edge here because we are dealing with latch. Okay? So start with Q equals 0. Then in this cycle, during the on cycle, S0, R0, which means hold. Then here there will be updates. Let me locate the updates. Okay. 0. Here is we are on hold. Then here set equal 1. This means Q will be 1. Then it will be on hold until the next cycle. Here 0, 0. Then we will be on hold. Here R equal 1, which means resets. We'll make it 0. Then here hold 0, 0. We will keep holding. Then holding here. Then here 1, 0. This means it will go up to be 1 because set is 1. Then it will hold. Then here 0, 0. Hold. Here 0, 0. Will hold, and that's it. Okay? Keep in mind, like, look at during the level, when the level is on, look at any changes in S and R. That's it. While otherwise outside of the level, which will be hold. Okay, how about the D latch? D latch, here's or with enable gates. Look at the gates. This is the on time. This is still also on. Locate at the on time. Then here, let's assume the initial condition 0. So the initial condition here is 0. So the first update locate at the on time. Here is the on time. What's happening on the on? It was D will be 0. Then here there are some changes happening. Then it will copy what's happening with D. Then here it will hold. Because here is hold, here is hold, and here is hold. The other one, D, D, D. Copy what's happening with D. So here we will copy what's happening with D. Then hold. Then we will copy what's happening with D. And that's it. Okay? Now, this one, falling edge flip-flop. D flip-flop. So falling edge, keep in mind falling edge means this one. So we will detect, falling edge here. We will detect what will happen only at this falling edge. So you need to write the guidelines only at these points. Then the rest will be holds. And I'm going to assume it as in 0 initial condition. So it will update only at this falling edge, at this guidelines. So here, it will hold. Then D here is actually equal to 1 at this edge, equal to 1. Then hold. D here equal to 1, hold. D here equal to 1, hold. D here equal to 0, hold. D here equal to 1, hold. That's it. So you see, the flip-flop is much easier. Now let's look at these models and determine what are those? Are those lights or flip-flops? How about this one? What's this? The first one. It's D and there is gates. Do you see any triangular shape? No, so it's latch. So what's this called? D latch, right? How about this one? SR latch, right? How about this one? Flip-flop. Is it rising or falling? Or positive or negative edge? Rising, yes. Or positive edge. How about this one? D flip-flop. Is it rising or falling? Rising. How about this one? SR flip-flop and rising, right? How about this? T flip-flop. And is it rising or falling? Rising. How about this one? D flip-flop and falling. Edge or negative edge. How about the last one? SR. Is it flip-flop or flip-flop, and it is falling. So you need to be aware of all of these. So it's a must. Because when you see this, it will not be given or provided to you. This one is flip-flop or this one is not. So you need to be aware of all of these. Again, rising or falling, if there is bubbles, these are falling. If there is no bubbles, rising. Okay, what else? Let's assume we have a rising edge flip-flop with the same scenario that we discussed before. So rising edge. Rising edge, look at all of these, rising edge. Then look at where the update will happen. Okay? Then here, there is an update happening here. D, or let's initial condition is 0. So it will start with 0, updates D will be 1, updates D will be 0, updates D is 0, updates D is 1, updates D is 0. Something like that. Yes? Maybe I'm bad in drawing them. Here 1, here 0, 0, 1, 0. Okay, so I need to be aware of this. Yes?
Like, what if it's going from a, 0 to 1, right as the line happens? Is that a 0?
Do you mean if it's falling edge? Or what do you, which one?
It's still rising edge, but, so the flip-flop is going, it goes from 0 to 1 immediately, right on the line. Would that be 0 or 1?
Let's assume, what's happening here, right?
Yeah, so that one's 1. If it was the other way around, would that be 0?
No, you need to assume it 1.
Assume it's always 1?
Yes.
Okay.
Assume it as always 1. Okay, any other question? So this example might take some time, so we will discuss this next lecture because we have a quiz. But you can try this and compare it with what we will see next lecture.